presentation will provide a short technical introduction to digital audio broadcasting, or DAB, as well as how DAB receivers can be tested using vector signal generators. DAB is the dominant form of digital audio broadcasting in most of Europe. It's also used in Australia and some parts of both Asia and Africa. The first European DAB broadcast was in Norway in 1995, and the longer-term vision is that DAB would eventually replace analog FM broadcasts. DAB is promoted by the World DAB Organization, and DAB technical standards are published by ETSI. One of the greatest advantages of DAB is that it allows multiple stations to share a single transmitter, making DAB more efficient in terms of spectrum use, transmit power, etc. Not only is a single transmitter frequency shared between multiple providers, but the total capacity of the transmitter can be flexibly and dynamically assigned. The other main advantages of DAB include better audio quality and the ability to provide data services. In DAB, a service is analogous to a station in traditional analog broadcasting. Each service is composed of one or more service components, which are audio or data streams. A collection of services is called an ensemble, which has a unique name or label. This ensemble can carry multiple services or stations from multiple networks. Our illustration here shows only 4, but a typical ensemble carries 9 to 12 services or more. As mentioned a few moments ago, each network has its own allocated capacity within the ensemble, and individual services can be dynamically assigned different bit rates. Generally speaking, lower bit rates allow more services per ensemble, but since this also reduces audio quality, lower bitrate services tend to be used for speech rather than for music programs. An ensemble is transmitted in the form of a signal referred to as a multiplex. A single multiplex carries a single ensemble and is transmitted on a single frequency with a bandwidth of approximately 1.5 MHz. With regards to deployment, multiplexes can be either national or regional. In most European countries, there are 1 or 2 national multiplexes and 5 to 20 regional multiplexes, although this can vary significantly between countries. In the case of national multiplexes, these are almost always so-called single-frequency networks, and this is a topic we'll cover in more detail in just a few minutes. DAB is most commonly deployed at VHF in Band 3, that is, frequencies in the range of 174 to 240 MHz. L-band frequencies could also be used where Band 3 is not available, or as a supplemental band in urban areas. But at the present time, L-band deployments are almost entirely trials or experiments. The center frequency of a DAB multiplex is usually called a block and is designated by a number and a letter. For example, block 5C refers to a signal with a center frequency of 178.352 MHz. Note that when using a DAB radio, the listener generally does not enter a station frequency the same way that analog broadcast stations are tuned. Instead, the radio receiver scans all blocks and then displays a list of available services from the detected or received multiplexes. DAB networks produce ensembles and multiplexes using 3 main functional blocks: the service provider, the ensemble/multiplex provider, and the transmission network provider. The interfaces between these blocks are standardized by ETSI, which enables the blocks to be developed and operated by different providers or entities. The service transport interface is used to carry the service components, that is, voice and data streams, and related control information, to a DAB multiplexer. The output of this multiplexer is carried over the Ensemble Transport Interface, or ETI, to one or more transmitters. The reason for saying one or more transmitters is because DAB can be deployed in the form of a single frequency network. Instead of having only one transmitter on a given frequency, multiple transmitters send the same signal, that is, the same multiplex, on the same frequency at the same time. This allows for more efficient spectrum utilization and also improves overall signal strength/reception. Single frequency networks do, however, require synchronization to ensure that the overall delay in the transport network, that is, over the ETI interface, is the same between the multiplexer and each transmission site. GPS is normally used for this task. Finally, note that individual transmitters within a single frequency network can optionally be identified using TII or Transmitter Identification Information. The DAB multiplex signal is transmitted using a special coded form of orthogonal frequency division multiplexing, commonly referred to as OFDM. In OFDM, the channel or bandwidth is divided into many separate but closely spaced subcarriers, each of which is individually modulated. Although these subcarriers are very close together, they are transmitted in such a way so as not to interfere with each other, and this is what is meant by orthogonal. One of the primary reasons for using OFDM is that it is robust against signal fading and other impairments caused by changing propagation, particularly in urban environments. DAB multiplexes can be transmitted using one of four transmission modes, which are usually designated by Roman numerals. These are predefined sets of OFDM and framing parameters, such as the number of symbols and subcarriers, carrier spacing, etc. The idea behind transmission modes was to allow the system to use different configurations when operating in different frequency bands and/or under different propagation conditions. However, the vast majority of DAB networks use Mode 1, and this is the normal mode used for most single-frequency terrestrial networks. Because transmission modes cannot guarantee error-free operation, DAB uses something called forward error correction to detect and correct bit errors. This is done by adding redundant bits to the data streams. Different protection levels add different amounts of redundancy, and this in turn enables the network operator to trade capacity, or bandwidth, for lower transmit power. The error protection in DAB can also be applied equally to all bits, or it can be applied unequally, such that more important bits have greater error protection. In addition, DAB uses interleaving to improve the effectiveness of error detection and correction. In particular, interleaving improves performance when errors occur in bursts that affect large numbers of sequential bits. DAB was relaunched in 2007 as DAB+, which adds the HEAAC v2 audio codec. This codec provides similar audio quality to DAB, but at much lower bit rates, and thus DAB+ allows more stations per multiplex with no loss in audio quality. It's also worth noting that while DAB+ receivers are generally backwards compatible with DAB, older DAB receivers are not able to receive DAB+ broadcasts. DAB and DAB+ receivers are most often designed and tested using vector signal generators to create user-defined DAB signals. The DAB signals are created and/or streamed in real time using data in the Ensemble Transport Interface, or ETI format, as discussed earlier in this presentation. This ETI data can be provided in the form of an internal file or may be streamed into the generator from an external multiplex server. The vector signal generator transmits the modulated RF signal to the receiver over a direct cable connection, or the signal can be radiated using an antenna. And finally, note that some vector signal generators can also add noise and/or interferes to the generated DAB signal, allowing for more realistic test scenarios or testing under challenging conditions. Let's end with a brief summary. Digital audio broadcasting, or DAB, is the predominant standard for digital radio in Europe and is used primarily in VHF Band 3. In DAB, programs from multiple providers are combined into an ensemble, and the resulting information is transmitted as a single multiplex signal. DAB also supports single-frequency networks, in which multiple transmitters send the same multiplex signal simultaneously. Like many other modern digital technologies, DAB uses a variant of orthogonal frequency division multiplexing, or OFDM, with configurable modulation parameters, as well as configurable forward error correction. The current version of DAB is referred to as DAB+, which introduced a new codec that improves audio quality and/or spectral efficiency. And lastly, we briefly mentioned that DAB receivers can be designed and tested using vector signal generators to create user-configurable DAB test signals. This concludes our presentation, Understanding Digital Audio Broadcasting. If you'd like to learn more about broadcast standards, how these standards are tested, or vector signal generators from Rohde & Schwarz, please see the links in the video description.